Uh, among news, we have that the last homework in the group of first exam is posted on iLearn. So the procedural programming homework is available on iLearn. That's the first thing. And second thing is that the midterm is scheduled for Monday, October 5th. So the idea is this one, that we do today and next week procedural programming, and then the deadline for procedural programming homework is on Friday, not this Friday, but next Friday. Okay, so we have like 10 days to submit that homework. And then you have Saturday and Sunday to relax and to refresh a little bit this syntax segment and data format segment, and come on Monday on midterm. And then after we finish that midterm, we have done with that forever. We are never going to repeat that again. We will start immediately after that logic programming and programming in Prolog. So this is going to be, from now on, will be only programming, not other things. So any question about that? And the deadline for this homework is tonight, midnight. So please submit it on time. There are.
I have a question, Professor.
Yes. Go ahead.
So just to make sure, you said once we take a test, that topic won't be covered again. Is that including the final as well?
No. Final is not comprehensive. So it is very important that we finish this segment of course now once forever. When we finish this, we have the new beginning of the new world of logic programming, and we are not going to have anything that we did so far on the final. So this is one and only exam that we have for this area. I don't see the reason to have midterms if you have that the final is comprehensive. Then you have only final if it covers everything. I think that it is easier to have exams in small pieces. We used to have actually not 3 of them, but 4, even 5. But we don't have money to pay grading. That's the problem. So the department is giving us 1 hour of grading per student per semester. So I don't have more, I cannot afford more exams. The number of exams is practically the number of dollars that I can use to pay teaching assistants, graders, and the maximum that we can have is these 3 exams. So that's all. Any other question?
Could you turn off the chime for when people join the?
Let me see how to do that. It is disturbing. Oh, you also hear that. So let me see. Record computer. Oh, participant. Video high. I don't see how to turn that off here. That's the problem.
It would be under the settings, but
huh?
It would be under the Zoom settings, but I wouldn't.
Zoom settings, I have to interrupt this presentation and set it from the beginning. So, ding dong, we'll do that next time, but today let us have it here. I remember that I've seen that tab somewhere, and how it remained turned on. It disturbs me as well. But anyhow, maybe it is good to disturb those who sleep. It is doing ding ding every moment. So, ding dong. As a matter of fact, we have now 66 people. So I have always approximately 15 people that are missing. And of course, I know who they are simply because you have a record of attendance that is kept by Zoom. I'll send an email asking people, what should I do so that they come? Not that I think that attending lectures is indispensable, but it is, or it should be useful. If it is useless, then tell me how to make it useful. That is what I can tell you only. Okay, so let us, yeah, it is not here. Okay, so specification of operators. You have to specify arity, type of operands for all of them, associativity rules, then how to write it in parentheses free notation, and what is priority of various operations. So first arity, of course, you have unary operators, those that have only one single operator, for example, increment or decrement or negation. You have binary, where you have operator and two operands. This is the most frequent case, assignment or operation, or insert or extract or shift. Ternary operations, they are only one practically, and this is this conditional expression where we have that condition can be true or false, and then we return either one or the other of these possible outputs. So arithmetic operators, of course, are addition, subtraction, multiplication, and division, and they're applied to arguments that are here sorted in a food chain. The smallest of them is 8-bit characters, then you have 16-bit short, and then integer, and then long, and then float, and then double and long double. Okay, so when you have any of these arguments, then for example, if you want to perform operation between character and float, character will be promoted to float, and then with float we perform operation. Operation, if it is arithmetic, is always done with arguments that are same data type. So those that are simpler are promoted to those that are more complex. So we have type conversions that are done automatically. If you say real equals integer, for example, int is integer variable, real is real variable, capitalized like this, this is going to create automatic type conversion from integer to real. If this real is double precision, then this is going to take time, and don't do that ever unintentionally. So this int here has 32 bits, and real has 64, for example. So you have to convert this into mantissa, an exponent. And this is a program that has 20 lines of code that is doing that. It is not trivial. It takes time. Don't do it without reason. If you have integer plus 0, you can provoke conversion also, because this 0 is double precision 0, and this integer will be converted to double precision. However, if you have integer equal real, all good compilers will give you warning, possible loss of accuracy. Because real, if it is 3.14, when you convert that to integer, it is going to be 3. So you're going to lose the fraction that you have, okay? And then here you have that if you put function int, then the compiler understands that you know what you are doing, and therefore, Peter, what's the question?
Oh, so how can we store primitive data types in computer, like at level or bits? So I just curious, do you have a header shows that the following few bits are representing an int or something?
Well, when you define in statically typed languages, so let us say you have that you use C++, which is statically typed language, then you have to say character A, B, C, D. So when you say character or signed character or unsigned character, these are numerical data types that have 8 bits. So from the name of the data type, you know how many bits you have. For example, if you say short is 2 bytes, 16 bits, and no more will be assigned. So that is the short. When you say int 40 years ago, int used to be 16 bits, but today is 32. Okay, so this is 8 bits. This is 16 bits. This is 32 bits. This here is 64 bits. Long double should be double, but it is usually 80 bits, no more than that, because it depends on architecture. So the float is standardized to 32. This is standardized to 64. This is standardized to 32, 16, and 8. So this is how you define what is the size of that. Okay.
But how can we cast them mutually?
Why would you cast?
So for some reason,
what is the purpose or reason of casting? Casting is something that is either done at compile time, but if you want something to transform in runtime, then you have functions. You have int. Int is the function that converts real to integer. And what has to be done here? Well, you have mantissa and exponent. And there is again program that is transforming this mantissa and exponent into integer format. For example, this here is 64 bits. And it has mantissa and exponent. And you have to make this exponent that is 0. And then you take mantissa and chop whatever can fit in this integer. So maybe it will fit, maybe it is not going to fit, because you can have too big number here that cannot fit in integer. And then you have overflow and all these things that happen. So there is no magic way that somebody will do something for you. You have to fully control each bit in your computer by understanding how is that implemented inside. And that's what we did in this data formats and in this homework. Hopefully this is understandable, I guess. Is that
yeah,
more?
thank you. Yeah.
Okay. So let us see conditional expression. If you have statically typed language, then this expression 1 and expression 2 must be the same data type. Otherwise, static typing will not accept like this, that you insert in output stream either string or double. This would be not acceptable because these are not compatible data type. They cannot be transformed to, from one to the other. But if you have here double and here you have integer, that is completely acceptable, because integer will be transformed into double if is necessary for some reason. For example, you can take this expression, if this is numerical and this is numerical, and multiply this by another numerical expression. This is going to be perfectly acceptable. Now, we have also dynamic typing. Dynamic typing means that this result is not statically typed like in this case. In this case, you have to put statically typed value in output stream. So compiler needs to know what is to be inserted in output stream, because if you insert something that is double, there is one way of inserting. For string, it is a different way of inserting. And in statically typed languages, this has to be equal data type. In dynamically typed languages, like Ruby, of course, this can be different, because this result does not have any data type. It is just the name of an object. And what kind of object is that is determined at the moment of evaluating this expression. So when you evaluate expression, what can come out is string, or can come out double precision number. So if it is string, then result becomes string, and that it has value, and it has also data type. So in the case of dynamic typing, we have that the type of object, this one here, is determined at the time of assignment of value. That means at runtime. Okay, so it can be either string or double. That's dynamic. Now, types of operands are always defined for each and every operator. So if you have operator extract, this one here, operator extract is defined so that on the left-hand side, there must be an input stream. It can be cin if you want, or input stream that comes from some file. That's also okay. On the right-hand side must be a variable. That means an object that is a variable that has index or no index, but cannot be expression. In the case of insert operator is defined that this here on the left-hand side must be an output stream, and this here must be an expression. And so this expression evaluates to an object, and this object is inserted in output stream. Of course, this is automatically done only for very, very simple objects. So character, string, real number, logic value, integer, that's what you can put inside, but nothing more. You cannot make an object that has 50 components and insert that in output stream simply because you must overload this operator, and you have to write your own overloading program to do that. You cannot do that automatically. If you can do that automatically, then this is what is called the first class language. This is like scheme. And that's the purpose for doing functional programming, because everything that is object of the language must be readable and printable. In C++, which is not first-class language, neither objects are readable nor are printable, unless they are very simple. Of course, you can read integers and floats and characters and strings, but you cannot read objects that have 30 components. So you have to write your own program that is doing that, which is not very convenient. So my question for you is, when you have this, what we have here, output stream, insert expression, what is returned by this expression? Each expression returns a value. So this pair of parentheses returns a value, and this pair of parentheses returns a value. What is returned? Is this a mystery, or you're just eating something so cannot answer? I suppose it is a mystery. So the mystery is solved this way. When you execute this operation, what is returned is input stream. When you execute this expression, what is returned is output stream. And this is perfectly visible when you have the story associativity. Associativity for arithmetic operations is left to right. All of them go left to right, except for assignment, that is right to left associative. You go from right-hand side, and you assume that you have these parentheses here and these parentheses here. You don't need to put them because this is assumed. However, in the case of insert and extract expressions, well, we have that this operation, cout insert n, is returning cout. Cin extract n returns cin. And as a consequence of that, we have this assumption that if cout insert a returns cout, then in this cout you can insert b. And then this expression from here to here returns cout. And then cout insert c is next. And then at the end, we return what? Again, C out that nobody uses. So when you write C out, insert A, insert B, insert C, insert D, this is going to return C out. Who is going to use that? Nobody, because you don't have more operators that would use this C out. But we have to be aware of that this C out insert A returns C out, because otherwise you could not write this expression. For example, if you cover this from here to here and say insert C in B, you are not inserting C in B. There is no doubt about that. You are inserting C in what? In output stream. Therefore, here must be an output stream if you have this operator. Therefore, this operation has parentheses, and each parenthesis, pair of parentheses, returns a value. C out insert A returns C out. And then next operation is C out insert B. And the last one is C out insert D. And this is associativity left to right. Same with C in. So you are not going to extract D from this C. You are extracting this D from C in. Therefore, C in extract A must return C in. Otherwise, you would not be able to write something like this. And this has to be crystal clear if you are writing programs that use files, because without that, you cannot understand how this works at all. Try to think always about associativity. Order of evaluation, we said that if you have insert operator like this, you are inserting A, B, C, D in this order. This does not mean that A, B, C, D are evaluated in this order. They can be evaluated in any order. You can first compute D, and then compute B, and then compute C, and then compute A. And then when you have 4 of them, then you insert them inside in this order A, B, C, D. So since you don't know in which order this is executed, it is not defined by the standard of the language. You cannot count on that, and you cannot make A, B, C, and D dependent on each other. For example, this B is changing a global variable that D is using. This is looking for trouble because if first D is executed to compute the value, then you are going to have, hopefully this is not Corona, otherwise you are going to have another teacher very soon. Let me go back here. This A, B, C, D have to be independent. That is what is the point here. And we studied that in this example here that you remember from last lecture. So I'm going to skip this. And we'll say a few words about parenthesis-free notation. Parenthesis-free notation is notation where you have to possibility to write all arithmetic expressions without parentheses, which is extremely important for compilation and for writing compilers. Now, this is invented by Jan Lukasiewicz, a mathematician from Poland, born in 1929. So he developed 2 notations, and prefix notation is notation where the operator comes before argument. So you say add A and B, and then multiply result and C. So you write in this way, multiply, add, so add A and B, you get the result, and then multiply A and C. This is called Polish notation. And the same situation can be done by reversing that, which is called reverse Polish notation, which is used by compilers. So if you have A plus B times C, you first put arguments and then put operator. So operand, operator. So you say A and B are operands, A operand, B operand, perform addition. When you get the result, operand C, perform multiplication. Well, when you have this, this is perfectly written for stack machine. So you say push A in the stack, push B in the stack, then add So push, push, add. When you add, you compute A plus B, and you have that at the top of the stack. Then push C. Now you have A plus B under C in the stack. And perform multiplication. When you perform multiplication, you are going to have at the top of the stack A plus B times C, and then pop that in X. So push A, push B, add, push C, multiply, and pop. This is directly machine language. So if you have a piece of code that is converting this parenthesized notation into reverse notation, then you have already done everything that is necessary for programming the stack machine. Push A, push B. Here is push A, push B, add, push C, multiply. And this creates machine code that is equivalent for this expression. If it is a little more complex, you have a little more lines, but it is exactly the same thing. Is this understandable? Any question? Okay. Let us say something about logic, operands and operators. All languages belong to two groups. In the first group are those who believe that it is necessary to have special data type. So they defined the logical data type, which is sometimes called Boolean in some languages. Logical data type has two values only, false and true. These are ordinal values. False is less than true. False is mapped somewhere to 0. True is mapped to 1. And then you cannot perform arithmetic operations with false and true. You cannot multiply them. You cannot do anything except and, or, and not. These three operations. Now, other languages like C say, you know what? Arithmetic 0 is going to be interpreted as false, and everything that is non-zero will be true. You do that way, you have advantages that combining arithmetic and logic data gives you more versatility and expressive power of language. This is good for professionals, and this is what is implemented in C. On the other hand, complete separation of logic and arithmetic operation is good for beginners because it contributes to safety. Okay, so you simply say, if it is logical, you have logical data type, and this is completely separated from numerical data types. You don't have these two things mixed together. Okay, so Pascal believes that it is good to have logical data type in that way. In some languages, like in Ruby, you have notation not and or, and not and or, both of them used. In C, C++, Java, similar languages, you have this for not and or. In Ruby, you have both of them, but this is low priority and this here is high priority. You will see that soon. Another thing that is important in arithmetic expression is the concept of short circuit evaluation. The idea is this one. It is implemented in C, C++, Java, but not in Pascal. So idea is shown here. Imagine that you have this expression A and B and C and D and E and F. So how to compute this expression? There are two possibilities. The first possibility is evaluate A, evaluate B, evaluate C, evaluate D, E, and F. So you have these values that are logic, true, false. Evaluate all of them. And then perform this operation A and B and C and D and E and F. That's the first way. In this way, you can have some advantages that compiler will have these binary things that can be done with binary operations, with binary AND, which is a kind of convenient to do that. And so in Pascal, they said the order of evaluation of this is compiler dependent. That means they don't tell you what is going to be the method of evaluating this, but you have to be able to provide A, B, C, D, E, and F before you perform this operation. In the case of short circuit evaluation, you have these arrows here. So the first thing you ask is A false? If A is false, you go out and never execute B, C, D, E, and F. If it is not false, if it is true, then you go and ask, is B false? If B is false, you go out and never execute C, D, E, and F. So this is called short circuit evaluation. Short circuit evaluation is that you propagate through these expressions as long as necessary to get the result and stop at the moment when the result is now. So if A is false, there is no reason to compute B, C, D, E, and F because the result is always going to be false. Therefore, this is what is called short circuit evaluation. Sometimes is implemented, sometimes is not. Here is example for OR operation. If you have A or B or C or D or E or G, then you have that if A is true, you go out and say it is satisfied without ever evaluating B, C, D, E, and G. Now, if you have short circuit evaluation, this is implemented like this. So if I have A and B and C, then if A equals false, then return A. So the compiler is taking this and transforming into this code here. If A is false, then return A. Else, if B is false, then return B. Else, return C. So if you return A, you will never evaluate B or C. Or if you return B, you are never going to evaluate C. And this is short circuit. Same is here. A or B or C. If A is true, then return A. Else, if B is true, then return B. Else, return C, whatever is C. So in the case, if A is true, you are not going to evaluate B and C. You are just going to evaluate A, and it is going to be enough. So this is the short circuit evaluation. So if I have if statement, like this one, if A and B and C and D, this is implemented in this way. So you write it in this way, but what is transformed inside your code is if A is false, put one temporary flag to A. Else, if B is false, put it to B. Else, if C is false, put it to C. Else, put it to D. And then, if this temporary is true, perform block. However, if A is false, T will be false. You are never going to evaluate B and C and D. You are going to go with false to this if statement. Since it is false, so we skip the block and drop to the next statement. So if A is false, there is going to be no execution of B, no execution of C, no execution of D, and no execution of block. Everything will be skipped. So from here, you go to this if and drop down immediately. So this is short circuit evaluation. Why we are talking about that? Because you need to know whether your language supports short circuit evaluation or not. When you encounter the new language, you can ask, are you supporting short circuit or not? Because if you are not supporting short circuit, like in the case of Pascal, where short circuit evaluation is possible, but not mandatory. So compiler designer can do it any way he or she wants. Then you have the following problem. Imagine that you have an array that has a number of variables defined as limit, okay, number of components limit. So the problem is to find whether specific value is in that list. So you have the search. You search the list sequentially from the first component to the last and ask, is this value inside? Okay, so we write that while I is less than or equal to limit and list of I is not equal to value, increment this I. If list of I is equal to value, you are going to drop from this loop, and you are going to have in variable I the component that is equal to value. So you are searching value inside this list or inside this array. Perfectly simple, trivial, one single line. However, this is going to work for all values that are inside this list. What happens in Pascal when the value is not in the list? Then at the end, you are going to have that this I is equal to limit, the last element in the list. So you ask whether the last element in the list is equal to this value. It is not, because there is no value in the list. So you increment this I, same as before. When you increment this I, you guessed what? List, a limit plus 1. So limit plus 1 is here evaluated versus this limit. And of course, it is not less than or equal to limit. However, Pascal is asking you to evaluate this before this end is applied. It is not short-circuited. So you come here with list of limit plus 1. And you are now out of bounds. So this is out of bound error. And you go out of bounds of your array, you create error depending on how compiler is adjusted, but you are going to have segmentation fault, segmentation error that is going to happen here. And this happens both with while do or repeat until. In the case of C, so this is unsafe program. It is not safe. If it is no value inside, you are going to jump outside of your array. And this is very bad. If you have that this is short-circuited, then if this I is greater than limit, this is going to be false. And you will never evaluate this here and never create this error. So in C, it's perfectly safe to say while I is less than or equal to limit and list of I is not equal to value plus plus I, nice. And if I is greater than limit, you are never going to come to put it here because it is short-circuited and you finish here. You never evaluate this here. Pedro, what's the question?
So to me, it seems like short-circuiting is always better and more efficient. Is that the case, or there's some scenarios where you would want it to check everything?
Yes, sir. It is better. And most modern languages have that. But it is not something that, it is something that must be part of the standard of language. So when they have logic expression, they must tell you, is it short-circuited or not? Because you write programs in different ways. If I know in Pascal that this is not short-circuited, I cannot write this line of code. I have to put here an if statement inside and say if I is greater than limit, I have to manually say to prevent that this here is evaluated. And it is written, it is up to compiler designer to decide how is this going to be done. Or you leave this as something that can be done for optimization. No, this has to be written in standard of the language. Short circuit is supported or is not supported. And when you say that it is not supported, then you have to do it yourself. And you can have this unsafe code, which works in 99% of cases. But when you go out of bounds, then you are in trouble. It is not going to give you the results. So it is necessary to have a short circuit evaluation implemented in the language. And if you have language where you don't know whether it is implemented or not, some new language that was yesterday invented somewhere in Silicon Valley, what are you going to do? You can ask, or you can never write code in this way because you don't know what's going to happen. Okay, so in C and C++, I tell you it is short-circuited, and okay, count on it, write this kind of code, it is safe because somebody will do that for you. Actually, they have this what is implemented always. They put these if, else, and it is creating, as the bottom line, is the safe code. Otherwise, there are those things that are left sometimes intentionally done in inappropriate way to have optimization. You remember this example that we had here. This example is showing you exactly one thing that is not written in the standard of the language. The standard of the language tells you nothing that these expressions are evaluated out of order. They say you insert this object one after the other. Beautiful. Who computes this object? Who computes that? Well, compiler decides of the order because it is optimum to go in this way. For example, compiler is looking this expression that if one of them can be reused, compiler will say, I'm not going to repeat this 2 times. I'm going to reuse piece of code, compute an intermediate result, put that in the register, and then take that from register to make a fast code. That's what optimizer is doing. Okay. So in order to give optimizer chance to optimize something, there are some things that are not read, that are not said in a proper way. So the way how you can judge that is this one. Take the textbook and look at this. A of n is n plus plus. Okay. Now, if they say avoid this because it is not safe, that's a good book. If they say nothing, or if they don't know at all that this can cause problems, then this is a bad book or a bad professor, whatever you like. So why? Because you have that you first evaluate this right-hand side. So you evaluate right-hand side, you have that it is n, and then you increment this n. So the question is this incremented n used here as n plus 1, or you perform a of n equals n, and then after that you come and perform incrementing? Okay, so that must be avoided because the result depends on compiler. And if you take Kernighan and Ritchie, the Bible for C, it tells you immediately, don't do this. Don't do this. It tells you that because if you have function plus function plus function, nobody guarantees you that this f is going to be done first, unless this is written in the standard of language. You have to say, if you have addition of 3 functions, the first will be evaluated first, the second will be second, third will be evaluated. But they don't tell you that. They'll tell you that if you have this value and this value and this value, it is going to be left associative. Okay, left associative, nice. So what? Is this meaning that you have to evaluate them in that order? Well, they say nothing. And then give compiler chance to go in opposite direction to do some optimization, and you are in trouble. So if you are warned that these things don't happen in the order they are written, but are inserted in that order, like in this example, everything is fine. But if they don't do that, then you are in trouble. So avoid trouble. The same is with this short circuit evaluation. Okay. Precedence of operators. Any other question? Precedence of operators. There are languages that have only one level of precedence. They go right to left in all expressions. Pascal has only 5 levels of precedence, which is considered insufficient. Fortran 77 has 10 levels of precedence, which is considered a good taste. Fortran 90 has 15 levels, which is less than good taste. C++ has 17, and Ruby has a gazillion of them, so which is more or less not particularly good taste. So too big or too small number of levels is inconvenient. Example of something that can be easily remembered is Fortran 77. Power function is performed first. Numeric multiplications and divisions are next. Unary plus or minus next. Numeric binary plus or minus next. And then character string concatenation. This is concatenation operator. And then relational operators, equal to, not equal. And then logic operation first, not. and then and then or. And then at the end, exclusive or, equivalence, not equivalence, whatever you have as logic operations are last. So this is easy to remember. If there are 25 of them, this is not easy to remember anymore. Okay. Now we are going to pay attention to performance of programs. And this is something that is very, very important because if you look what happened during the previous 30 years, we had that Moore's law was working. Practically, what was happening is that each 12th month, you have that price performance was doubling. That means that you had that when you buy new computer, it is always 4 or 5 times faster than your previous computer. So computers became more and more fast. And then Wirth said, software is getting slower more rapidly than hardware becomes faster. And this is something that all older people know, because over last 40 years, the quality of software is deteriorating. Software is becoming worse and worse. More and more programs that are written by people who don't understand what's going on at all and produce software thinking that if it is slow and it works, that's okay. If you need it faster, buy faster computer or select faster processor or increase clock rate. If it is too big, no problem. We have gigabytes of memory. Well, there is the end of that case, of that period, because no exponential function was living forever. That's the rule of universe. Okay, so in programming is the same thing. So people tend to pay little attention to performance. And now performance is becoming more and more important, because no matter how rich you are, you cannot buy a processor that has 50 gigahertz clock. You can have processors that have 3 or 4 gigahertz, but no more than that, okay? Because we are hitting in some limits. So faster processors were practical invitation to lower quality of software and less thinking. Do it brute force, do it any way that it works and it's done. Well, this is something that I want to fight against for at least a week and a half. So starting right now. So what are performance indicators? First, the idea is produce result with minimum use of resources. And resources are processor time, memory size, disk file accesses, disk file size. So try to write your programs so that processor time is used to minimum, so high speed. Memory size, compact data and compact code. If it is short, it is going to be also fast. Do not access disk without reason many times, and minimize the file size if possible. Can somebody tell me how to minimize the file size?
You can do things like minifying your code, which removes unnecessary characters and makes it smaller.
How about data? Yes, how about data?
Don't use like an int if you don't need an int, for example.
You can use something else that is saving time, for saving space. For example, imagine that you have a file in C++ and you want to insert inside pi 3.14, etc. Okay. If you insert that in file, what is going to happen? You're going to insert the same way you insert that on the screen. So you're going to have ASCII characters 3, dot, 1, 4, etc. Each character will take 1 byte. And when you put something that has 10 bytes, okay, this is going to be your pi. If you put that as float number that is used with binary transfer without converting from binary to character, you are going to have for float only 4 bytes, and it's going to be pi inside. So when you have disk write operation, it is either doing that the same way you do on the screen, or it is taking binary transfer. Binary transfer saves memory and saves conversion time, because in memory, everything is done as mantissa and exponent. Okay, so why to transform that mantissa and exponent into 3.14 and have this string that you are putting on disk or putting on screen? On screen, you have to put it as the string, because this is for human consumption. You have to read that. Humans don't read mantissa and exponent. But when you transfer that to disk, why to convert? That is waste of time and waste of space. So this is awareness of disk file size. So you have to do binary transfer. That's the answer. So we try to promote performance awareness, even for smallest programs. And let us, this homework that you have, the last homework before the midterm, this is having this kind of reasoning that is developing. So how to make things fast and compact. And so there is also one assignment that is measuring the speed. So this is one that is going to be interesting. I'll speak about it in a minute. So we always have that we have to balance performance and cost. So performance has to be maximized if possible, if we can afford. So what kind of performance we have problems? First, order of complexity. So if you have sort, you have bubble sort that is O of n square, quadratic algorithm, or quicksort, which is n log n. And of course, n log n is much better than O of n square. So we have to try that. And then performance of algorithms has criteria: maximum speed, minimum memory consumption, minimum complexity, readability, reliability for wide range of input data. So these are criteria that we try to keep in mind all time when we develop algorithms. And let us start by showing examples. Of course, we will use the big O notation, which you know from previous classes. So if I have a simple program that is having to sum components of an array, so you have from I0 through n minus 1, then you are adding sum plus equals a of I. So this is executed n times, and the time is constant times n. So this is linear algorithm. Time is O of n. O of n means that it is order of complexity linear. The most popular of all linear algorithms on this planet is payroll. Whenever I ask what is the most frequently used linear algorithm, it is always payroll. For all people who work, you have for all companies to print each time paychecks or to process payments. So you go from one employee to another employee. If you have 2 times more employees, your program will run 2 times more. This is a linear algorithm that is proportional to the number of people in the company. More people, more time to make paychecks. So this is a linear algorithm. The food chain looks like this. You have first algorithm that take constant time, like our friend square root that we did for this homework today, that is due today. Then you have logarithmic algorithm like binary search, then linear algorithm, plenty of them, like payroll, then n log n, this is quicksort exemplified, quadratic algorithm, everything that has 2 loops, one inside the other is quadratic, therefore you are going to have that select sort or bubble sort or insert sort, or 3 of them are quadratic. Power function is when you have k loops, one inside the other. So for example, matrix multiplication is cubic algorithm. And then you have exponential, factorial algorithm, all of them that are non-polynomial cannot be executed on current computers except for trivially small values of n. When the size increases, this is not acceptable, and you will see examples. So we try to develop a program that has lowest time complexity. That means to be as low in this table as possible. And if you have two of them that have same complexity, then to find the minimum value of n. For example, if you have bubble sort and select sort and insert sort, all three of them are O of n squared. So you have constant times n squared. Of course, these constants are different. So bubble sort and insert sort and select sort are not equally fast. Some of them is the fastest. When you take these three programs, you can write them in various ways. For example, in the case of select sort, when you have that you go through the array, find the minimum value, put it at the beginning. Then take minimum value from the rest, put it at the beginning. And this is quadratic algorithm. And it is slow. It is something like square. However, I can go zigzag. I can go from first component to the last and put, for example, the last value at the end, and go zigzag from the one before last to the first, put the smallest down. So go zigzag, 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 finish in the middle. It is also quadratic, but it is slightly better than if you go all time in the same direction. So C has to be adjusted as the minimum value if you have the same order of complexity. Example of constant algorithm, one that takes constant time, is swap. So I have here swap function. I want to swap x and y. So I have to pass them by reference. That means x and y do not exist in this program. They are somewhere outside, and I give the address of them to this swap function. Swap function has internally an object that is same data type of this here. So put this x in this temporary, and then from y put in the x, and then from t put in the y, and go out, and you will have contents of x and contents of y that are swapped. So the question is it possible to swap without using temporary? This one here. Yes or no? Well, it is not a big question since we have it here. The answer is yes. Yes, but let us see how this works. So I have here two integers, same as here, integer x and integer y. I want to swap them. So what I compute here is x plus y. So you have the sum in x. Then you say sum minus y, which is here, is giving you x. And this is now stored in y. So y is now x, and x is sum. So sum is sum minus y is now giving you y, because in y there was x, and therefore x becomes y. So this is making swap without temporary variable. I swapped these two integers. So the question is this program correct or incorrect? Is it good or bad? What do you think?
I think it's bad. What if you add x and y and it overflows?
Well, it is either bad or terribly bad. That is, these are two possible answers, and you are, sir, perfectly correct. Yes, it is a very bad program. The question is, what are the reasons why it is bad? The first thing is it is not very readable. It is a kind of tricky, because you have here that x is not x, but it is the sum. This y is no more y, but it is x. And then this x is no more x, but it is y. So you have to think how this works and how you push. That's the first thing. But that's not the worst thing. It works only for data types that support addition and subtraction. So you cannot swap two objects. You can swap two integers, two characters, two floats, and two doubles. And bye-bye. That is what is done in this way, because this is what you can add and subtract. Next thing, it can cause rounding errors for float and double, because if you are adding things, it is going to round them somehow. So it is not going only to swap, but it is going to round and change the value. It is not safe. If you have integers, it is going to create overflow. When you add two things or subtract two things, you can create overflow very easily. So adding this x plus y, if you have two big numbers that you have to swap, so that are close to the limit of integers, you add them here and you immediately have the wrong result. So you are in trouble in no time. So that is not safe. It does not work for arbitrary objects. And finally, avoiding this t is giving negligible benefit. This t is not taking huge space that you are now making big thing that you avoid using t. So this is nice to spend good time on a beach, you know, and you ask your significant other, can you do swap without t? And then that's the beach question, but not for programming, because it is certainly unacceptably wrong algorithm. So there are other constant algorithms. For example, one that is computing time. You are going to use this one. You take clock, divide by clocks per second, and get the number of seconds from the beginning of counting, which is January 1970. And then you can use that to measure how long does it take to execute a piece of code. And you will have that in your homework. Random number generator also runs for always the same time, regardless what is the number. This is number between 0 and maximum value. And then when you divide that by random max, you get from 0 to 1, a uniform random number in the range from 0 to 1. Square root is also running for the constant time. Actually, they have two iterations. If you take this book, by the way, I had it here. I don't know, have you seen this one? It's called the Standard C Library. Okay, so this book has inside all programs. If you want to see how is square root done, you have code written in C. So you see what is inside. And if you take square root, you will find that square root is implemented by two Newtonian iterations. They don't put that in loop at all. So we were using here the loop. You know, I was doing do while this here. They have this that is applied twice. And before that, they make polynomial approximation. So this is something that is giving you a fastest possible execution, faster than what I have here. But if you have time, take a look how is this implemented. An example of linear algorithm, array initialization, put random numbers in array. So first randomize a random number generator, put random seed, and then put here loop that is filling array with random numbers. Of course, random is unsigned integer. Modulo 100 gives you all values between 0 and 99. So you are filling this with values 0 through 99. Finding maximum value, going backwards, for example, while minus minus n is greater than or equal to 0, perform this operation if it is greater than m is a of n. So you can do it in this way. To avoid putting this in a for loop, you can always use while loop, where this index is used as a counter at the same time. Linear algorithm, computing mean value, add all components of array, divide by n, linear algorithm again. And then factorial. Well, with factorial, we have two possibilities how to write it. This is nice, theoretically sound, and elegant way. So you say, if n is less than 1, which means 0, return 1. In all other cases, return n times function of n minus 1. So jump to this function again and use it with argument n-1. This is a recursive version of writing this program. You can write this program also iteratively. You can insert inside two variables that are completely invisible in the problem statement. So you have that this f and this I, so this is accumulator and this is counter. So I go for I is 2, 2n, and then compute f is f times I, and then increment this I. Now, when you are given factorial function, nobody is telling you that you need some accumulator and some counter. The function is defined this way, n times n-1. That's f of n. So practically this here is a non-procedural program. I say nothing about procedure. Recursion is automatically creating procedure because you are practically pushing this n-1 in the stack as argument and push, 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 and then perform operation, multiply, multiply, pop, 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 pop. So this push, 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 pop, 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 pop are taking space and time. Therefore, therefore you have that this is correct, non-procedural, and simpler than this one. This one is difficult. This one is simple. That has to be more than clear to everybody, I suppose. It's a single line. You don't know programming whatsoever. What you are writing here, definition of the function. So where is the programming effort? Zero. Do nothing. Just write the definition of function and it comes automatically. Here, you have to be a programmer. You have to know that you have to introduce two variables that don't exist in this problem. Okay, so you are introducing two new variables. You are using the loop, multiplying and then returning this accumulator f. So this is iterative, this is recursive. The question is, which one is faster? Usually, the iterative is faster because this filling the stack and emptying the stack takes time. And you have also to transfer all these arguments. That does not exist here. Here, you just have this addition and this multiplication. That's all what you do, nothing else. So it is a little bit faster than this here. But this program here and this program here, both of them are linear O of n. So these are both of them acceptable solution. And this one, if it is not critical, is much better for humans because it is easier to write this than to write this here. Okay. Now, linear algorithm can be in multiple variables. So this is one beautiful algorithm for merging two arrays, A and B. Read it when you have time. It is time is constant times NA plus NB, the size of these two arrays, array A and array B, that have to be merged. Of course, these are sorted arrays. Now, how about logarithmic algorithms? When they happen? Logarithmic algorithms are something that we very much like because in each iteration, we are dividing the problem in two. And so this is binary search or recursive binary search. You have these two algorithms as your homework, and this is the only case that I know where recursive binary search was faster than the iterative binary search. However, you have also linear logarithmic algorithms. These are those that are based on dividing by 2 in each iteration size of the problem, but each time you go through all components of the array, which is practically what happens with quicksort. And we also have quadratic algorithms or things like matrix multiplication, which is a cubic algorithm. Here it is. It has 3 loops. Loop that is going 0 through n, 0 through n, 0 to n, and therefore n times n times n is n to the 3rd degree. This is very good for benchmarking. We are going to use this program for benchmarks. And there is also possible to find algorithms that are exponential. And as an example of that is Fibonacci numbers. Fibonacci numbers are a sequence where each number is sum of two previous numbers. So this number is previous number 2 plus 3. 2 plus 3 is 5. 3 plus 5 is 8. 8 plus 5 is 13, and so on and so forth. And you start with 0, 1. Now you can be tempted to write this program. So if n is less than 0, return n. Otherwise, return f of n minus 1 plus f on n minus 2. This is elegant, short, non-procedural, and theoretically correct program, which is otherwise completely criminal. Unaccepted. If you write something like this, they are going to put you in San Quentin to stay for at least 2 months. So don't do it at all. For what reason? Because if you want to compute what is the time necessary to compute this, the time is time of n, is a little time that can be neglected for this if statement, plus the time for computing a function of n minus 1, function of n minus 1. So you have that t of n is t of n minus 1 plus t of n minus 2. Therefore, after we try to solve this functional equation, and we try to solve it by using these two constants, c and g, to exponent n, when you insert that in this functional equation, you get this expression here. Then you can cancel with cg to n, and you get this quadratic equation. Solve quadratic equation, you get that g is 1.618. Therefore, time for this program is 1.618 to n. It is exponential algorithm. And I usually tell you my experience with this algorithm. If you have a machine that performs approximately 1 million operations per second, and that was VAX 750 that I used to have years ago. So 1 million operations per second. And you want to compute Fibonacci of 32. So to add 32 these components. Could you guess how long does it take? Most likely not. It takes 7 minutes. 7 minutes to compute Fibonacci of 32 for case where you have 1 million operations per second. Unless you are completely drunk, you would be able to add these 32 numbers with pencil and piece of paper for less time than 7 minutes. Can you add 32 numbers in 7 minutes? Come on. Obviously you can. So you are with pencil and paper faster than machine that makes 1 million operations per second. So this is not acceptable. So what is acceptable? Well, what is acceptable is iterative program, which is linear algorithm. It is not exponential algorithm as this one here, and gives you result in a few microseconds. But then you have to write your own iterative procedure, and you have to introduce auxiliary variables, counter, and 0, and first, and second, that are not visible in the statement of the problem. And you have to say second is first plus 0, then you have to shift them, and then you have to go through the loop to do that. Well, this is iterative solution. It is linear, it is very fast, but it is ugly and not completely easy to write. This here, of course, is extremely easy, and it is theoretically correct, but it is unacceptable from the statement of performance. And this is all that we are going to study today. We'll go from here next time, but try to think about this and read this and make this experiment if you have time, and you will see how terribly slow this function is when you have n that is not trivially small. This is exponential algorithm. It is not as bad as 2 to n, but it is 1.6 to n. It is 2 to n is something that is doubling time when you add 1. So when you add 1 to n, you have that the time is increasing. So that's all what we have for today. If you have some questions, go ahead. Otherwise, office hours are from 1 to 2. Any